I should start.
Yep. Okay, so we are live. Hello, AI and deep learning enthusiasts. I feel like we've been on a break for a little while here due to the workshop and some other things going on, but we are back now today, and this is the online discussion of the deep learning book. So just some background information for people that are joining us for the first time. We are the AI and deep learning enthusiast group out of San Francisco, and we are covering the deep learning book chapter by chapter. And this is kind of a community-run fun learning experience. So what we do is we have a volunteer presenter sign up each week that gets together and reads all of the material ahead of time, puts together a presentation for us. The presentation can be between 10 minutes and 2 hours long. So usually it's about an hour. And we simply ask them to review the material that was covered to kind of supplement the learning experience that people get from reading the book. And if you'd like to sign up to be a volunteer presenter, you can do so by joining our meetup group, and that's the AI and deep learning enthusiasts in the Bay Area. But we have a link for a presenter sign-up form, and there's two sheets. There's the online, if you look at the tabs at the bottom, there's the online section and the in-person section. So if you'd like to present with us online on YouTube, you can just click on that link for online. If you'd like to present in person, we also meet in San Francisco at Sandbox Suites. And we'll also be starting a new meetup soon in the East Bay as well. So I'll give you more information about that shortly. And yeah, so we want to introduce our volunteer presenter today. He's been with us for a while and has presented a couple different times. So we have Pankaj with Data Cabinet, and he'll be going over chapter 13 today for us.
Thanks, Laura.
Yep.
I'm Pankaj Kumar. I've been part of this deep learning community for a while. I'm very enthusiastic about deep learning. And today's topic is linear factor models. So a high-level overview is that I hope it's okay to get started, Laura, right?
Yes, yeah, please go ahead.
Yeah, okay. So so this is mostly a unsupervised method where given a set of data, you're trying to figure out, like in unsupervised methods, you're trying to figure out a model on the data. So given a bunch of points with different features, you're trying to figure out what is the probability distribution that given some data, some features, you can predict the rest of the features. So, but there is this thing called latent variables. So think of it as, for example, if you are given Netflix data and you're given a set of users and the movies they like, and the movies they like could be like in the millions, but the actual set of variables that explain which movies you like might be less than a million. So for example, your age group might determine what movies you like, or your location might, or the language you speak might determine what movies you like. So they are generally called latent variables. So this latent this is, so the way, if you're given a bunch of points, this linear factor models can be also thought of as a study of these latent variables. And if you see, the model on the data can be also represented as this expectation over h, where h is generally a lower dimensional point or an encoding of the actual point. So for example, in the Netflix data, h is the age group or language, and you can sum over all h's for the probability of x, and that expectation will actually give you the probability distribution of x. So this is just factor models. The term linear comes from linear factor models. So generally, the way factor models are done is this WH plus B. So once you have identified the factors H, there are two directions to it: going from X to H and going from H to X. So when your model assumes that going from H to X, you are going to do a linear transformation. So WH plus B plus some noise, then it's called a linear factor model. So if you think here, H, the number of dimensions in H is equal to the number of dimensions in X, but it could be different. So you take H, you apply a linear transformation to get X. And there are various methods we can do this. And this chapter goes through them. Goes through them. And the various methods generally play on what is the prior on H that is assumed, PH, and what is the noise, or there could be even no noise. So so we'll go to the first variation. So the first variation is factor analysis, which is a pretty generic one, in which the distribution that is assumed on H is a unit distribution, so unit normal distribution. So you can have a H which is comprised of a bunch of HIs that are all unit normal, and then the transform you can assume is one second. The noise is assumed to be assumed to be a diagonal. So all H's are X is So given H, if you are, the assumption here is that if you take a bunch of H's, so H1, H2, H3, like here, then when you do a transform to X, so like here, then given a set of H, X1, X2, X3 is conditionally independent. So that's the basic assumption in factor analysis. But also that the different X's have there is a noise, I think, of different. There's a diagonal noise, I think, that gets added to that can so that has different elements on the diagonals, but rest of the matrix is 0. So that's factor analysis, and then probabilistic PCA is a small variant on factor analysis. So if our assumption is that the noise that gets, I think it is noise. I'll double check though. If this noise is all the same, if we assume that this is all sigma square, then we can say that then it becomes a probabilistic PCA. So in probabilistic PCA, we are trying to model H such that X is WH plus B plus a unit normal Gaussian noise. Right? Yeah, I think Z is also a unit normal. I think I missed it in the book. Let me go back to the book and see. So yeah, Z is also a unit normal. So
you're doing great. We don't have any questions in the chat yet, so don't worry about that.
Okay. So now probabilistic PCA is when you are modeling WH plus B plus a unit normal with sigma. But the regular PCA that we study is like is the special case of probabilistic PCA. So probabilistic PCA is a special case of factor analysis, and PCA is a special case of probabilistic PCA. When you put this, when you think there is no noise. So in that case, you can just see the way you model is just get the principal eigenvectors, and then you make a projection on those eigenvectors, and then you can get the various components. Then you can get H that explains the most variation, So that's the PCA part. And then the next, so all these methods are assuming that that the input, the condition, that given x is pairwise independent. They're not assuming that given x is mutually independent. So in independent component analysis, what happens is, wait, is this the slide? So wait, no, I think okay. So in the independent component analysis, I'm sorry, I think H is the way H is modeled is that H is, we try to get an H that is mutually independent and not pairwise independent. So they're all independent variables. So the example that the book gives is, for example, in independent component analysis, if you have 5 speakers, 5 microphones in a room of 10 speakers, like 10 people who are speaking, then and you can record the observations on the microphone, then those are going to be generated by 10 individual speakers. So that is, I think I put it in the opposite order. I think this is individual speakers. This is microphone output. So in PCA, we are going to study how the individual speakers with, yeah, that's right. So how given the output from the microphone, how we can get the signals for the individual speakers. So that is something, and we are assuming that the things spoken by the speakers are all mutually independent, not pairwise independent. So no two of them are related to each other. So that's so that's independent. And in independent component analysis, generally we are just trying to. So there are various variations of independent component analysis, and one of them is generally the way it's done is generally it's not a generative process. So we are not doing we are not trying to figure out a px given a ph or assuming a ph trying to find a h. We are just generally trying to find just this transform w that best explains, given x, w inverse x explains h. So and then also, so some variations of this are sometimes you can add a noise, like in factor analysis to x. And there is also this problem that, wait 1 second, let me. So there is also this problem that if you, for example, this is variable substitution. So if you, for example, generally it's not done for probability, but if you get a distribution in H, and if you want to get a distribution on X, then you have to it's not a simple substitution. You have to find out the determinant of W. So to find out the determinant of W is sometimes an expensive operation. So the way we find out, so if you also impose a condition that all the columns of W are orthogonal to each other, then you can see that the determinant is going to be 1 or -1. So because if you multiply, if they're orthogonal and normal, unit orthonormal, then if you multiply W by W transpose, it's an identity matrix, and W and W transpose need to be integers, and so they can either be 1 or -1. So determinant of W. So that makes it easier to find the determinant. And So also that the training for like probabilistic PCA, or if you see for probabilistic PCA, the way we find out W and sigma is through expectation maximization algorithm. But in ICA, we generally don't, like sometimes they don't train on maximum likelihood, but the way you train is to make H independent of each other. So H, so if you remember, the ICA has the assumption that all H's are independent of each other. So when you encode X to H, W is chosen such that H is independent of each other. And so also that if in this one in ICA, PH is assumed to be non-Gaussian. The book claims, and I don't think they give a proof of it, that if PH is independent prior with Gaussian component, so if it has like second moment, first moment only, then W is not unique or identifiable. There could be many different W's that can satisfy, that can make H to be independent. So but if you see the other ones, the other like the initial ones we discussed, the probabilistic PCA and factor analysis, there the prior on PH is Gaussian. And they have closed form solutions that way.
Also, can you describe when would be the best time to use an ICA in the different variations?
Well, depending on the, so if you, I think there is a, okay. So if you, the book gives an example, like if you, for example, know that the underlying signals are independent, and not just mutually independent, they are independent, then I see like in the example, like in this example, right, that you know that the individual signals are independent, the individual signals that you're going after are independent, then you want to use ICA over regular PCA or probabilistic PCA.
Great, thank you.
And so also there is this thing yeah, so there is also this if you, so there's this thing kurtosis. So kurtosis is like mean, variance. Kurtosis is like the third, mean is the first moment, variance is the second moment. Kurtosis, I think, is the third or fourth moment. So so like it says, ICA requires that pH is non-Gaussian, and Gaussians are determined by first moment and second moment of a random variable, and generally like so what I understood of it is, like if you try to figure out a W such that H has a high kurtosis, then pH is non-Gaussian. So so this is one way to figure out H. So the way you train H given X is you try to find a W that gives it a W inverse that gives H a very high kurtosis. So that is one thing that the book mentions. And so that's all about. I think I felt like the book does not go into like the total detail of this. It went through an overview of the material. So if you are looking for like exact formulations, so for example here they do mention that these things have closed form solutions, but the book does not give the closed form solution in factor analysis and probabilistic PCA. They just give an intuition of what it is. So and then there is slow feature analysis. So you can think of slow feature analysis also as a feature extraction method. And the assumption here is that, for example, if you are given like a time series of like a video, like a bunch of pictures in a video where a zebra is moving from left to right, then the individual pixels in the image are changing very rapidly. But if you, for example, know what is the location of the zebra, XY location of zebra, then that is not changing very rapidly. So if, for example, you had a function that, given an image, gives you the exact location of the zebra in XY coordinates, then that location is changing slowly with the velocity of the zebra. So here in slow feature analysis, we are trying to find those XY coordinates intuitively to extract features from the image. So the way we do it is here, for example, you impose a loss function. So f here is basically takes an image and think of it as f takes an image at time t+1 and gives out a XY coordinate. And similarly, fxt takes an image at the tth time and gives the coordinate of the zebra, XY coordinate of the zebra. And this is a L2 loss function. So you kind of subtract and square and put it as a loss function. So if f is parameterized by theta, so let's suppose f is some if theta is some parameter and f is a function using those parameters, then if you train on this loss function, then you can achieve the best theta that gives you that extracts the location of the zebra from an image. So this is the idea behind slow feature analysis. So there are some things that the book mentions. So for example, here we are also assuming that the mean of the coordinates that slow feature analysis gives is going to be 0, because if it's not 0, then you can always add, because if you see, this is subtracting one function invocation from another. So if you do not impose this mean to be 0, then if you increase both by a constant amount, then the function will still have the same loss. So this constraint removes that possibility.
Hey, Pankaj, we have a quick question from the chat.
Yeah.
So Sharif has asked, and this is going back to ICA, isn't it correct that ICA is used to specifically separate multiple independent sources of signals, such as recovering the sound from each speaker in a multi-speaker conversion?
That's right. That's what. There are other examples in the book as well. So one example that the book gives is if you have multiple electrodes that are measuring signal from your brain and your heart and your eyes, then you can take the signals and use ICA to figure out the actual signal from the brain and the eyes and the heart, I think. So this is the underlying. ICA is assuming underlying independent sources.
Great, thank you.
Here. So recap. This we are trying to optimize this. F takes image, gives output as a couple of coordinates, and F is a feature extractor, and we are trying to minimize an L2 loss on fx. Given we are trying to find the theta that will minimize the L2 loss. So first constraint that we have to put is that the values of fx, the mean of those values are 0. The second constraint is that the the squares should sum to 1, because if they don't sum to 1, then what happens? Yeah, if okay, I forget exactly. Let me go back to the book. Okay, if they are not 1, so if the expectation of these features is a square is not 1, then you can just have this fx output 0 for everything, and then the L2 loss will be 0. So we want to prevent that. So we make sure that each of these components actually sum to 1. The square of each of these components sum to 1, so that it has to output a non-zero value. So that's, and then there is another constraint that the expectation of fxt, the individual. So if, for example, your slow feature analysis gives out x and y coordinates of the zebra, let's suppose, and the x coordinate is moving very fast and the y component is moving very slow, then in this case, what it can do is it will only find the y component and not find the x component, because y component will give a smaller value for the loss. So so what we want to do is we want to impose another constraint that so we want to add another constraint that the expectation of the two values should be 0, which means that the two features, x and y coordinates of the zebra, need to be uncorrelated with each other, because if you just take the y component, let's suppose the y component is moving slowly, x component is moving faster, and you just take the y component and put x as all zeros, then they will not be mutually uncorrelated. So if you impose this condition that x and y need, like all features that we learn are mutually not correlated, then we'll find both x and y. So that's the intuition behind it.
We have another question in the chat room. So Sharif has asked, how does 13.9 constraint ensure that the problem has a unique solution?
Well, 13.9, if you see, if you, for example, add a constant to both of these, right? Then this term is still the same, right? Mm-hmm. So you don't you want them to have you don't want them to have different. If you don't apply this constraint that the expectation of them is 0, then the expectation of each one of them is 0, or mean of each of them is 0, then you can just shift each of x by a constant amount, and you will get a solution with the same same loss value.
Hey, I have a question for you too. So I was trying to look up images, because to me it always makes more sense when I have something visually to compare this information to. So for example, I'll just share my screen as well, so people can see this really quickly. So for me, can you see this image right now on my screen?
Yeah.
Okay, great. So it looks like there's incremental slow feature analysis as pictured here, but then there's also this probabilistic slow feature analysis. Can you describe the main difference between the two?
I don't think the book mentions probabilistic slow feature analysis. I don't know what it is exactly.
Yeah, so okay, so is the incremental more closely related to what the book is describing in this case?
Yeah, I think they all have various variants. So the book is describing like an overall idea of wait. So apply temporal to spatial transformation. Mm-hmm. Apply learned features.
So is this not close to what the the book is describing.
I don't know the context behind it exactly.
Okay, so
the book.
I was just going to say, if we can find an image that might describe this better for our viewers as well, I feel like that might be helpful. Because I know, like I said, me personally, it helps when I have something visual to compare this stuff to.
Yeah, I don't think the book gives any images, because I take all the images and put it on the presentation. So
okay.
Wait.
Well, we can come back to that. Maybe we'll try to find one and share it to the group.
Sure. See, I don't see any images.
Yeah, that's perfectly fine. You can continue, okay. Pankaj. Yeah.
Sure. Okay. So then, slow feature analysis can also be used to learn non-linear features. So you don't really and you can have like a deeper network as well. So the way you would do it is basically you apply, you take your x's, you do a nonlinear basis expansion. So you take x square, x1, x2, x2, x3, x2 square, all those terms. So that becomes a nonlinear basis. And then you apply SFA to that basis. And you can even do it incrementally. And then the output that you get, you can apply another nonlinear. So x, you get an h. Then on that h, you can again do a nonlinear transformation. So for example, from your h, you get you put a nonlinear transform. You take x1, x2, x1 square, x2 square, and then you get h1, h2. Then you again do h1 square, h2 square, h1, h2, and then you again run an SFA. So it can even have a deeper model, and also it can have nonlinear features. So and the book gives a couple of biologically occurring examples. So let me open that. I think I had it open. So it says that when trained on a small spatial patch of the SFA with quadratic basic expansion learns features that share many characteristics with those of complex cells in V1 cortex. So it seems SFA is possible, biologically plausible, and okay. And I'll go back to the presentation, and also. So one thing is also there, that SFA is sometimes able to present theoretically. So if you, for example, have a 3D scene from a camera, and you know that the camera's velocity and camera's location is predicts the scene pretty well, then SFA is able to get the camera's position and velocity. So that is like without explicitly coding needing that. So that is a major advantage of slow feature analysis. But also that but slowness principle has a prior that it assumes that the changes are because the underlying things are changing very slowly, but that might not be the case. So and that's why it's not very it's like it has limited performance. So the book says a better way to a better prior could be that one position determines the next position, not the slowness criteria. So that's what the book says, that it's not very useful practically. So next we come to sparse coding. So in sparse coding is also a linear model, but the way it models is slightly different. So if you see, if you see the okay, so first of all, it assumes a prior on H, like it assumes a prior on the so let's define two terms. X to H is encoding, and H to X is decoding, let's suppose. So then it assumes that P of Hi is a Laplace distribution. So Laplace distribution has a peak at 0. So so that, and there are other like Cauchy distribution that gets used, which is also has a peak at 0. So this and also, if you see the way X is modeled on H is that the mean is WH plus B, and there is a noise of 1 by beta I. So now, and in sparse coding, we are not trying to find a W to go to encode or to encode. So going from X to H, generally, if you see the other methods, we are just multiplying by a W. But here we are not multiplying by a W. We are actually running a full algorithm to find the H, where it predicts it has the maximum probability of H given X under the prior that H is sampled from a Laplace distribution. And then if you expand this argmax, then you can write argmax P H of X as argmax X given H multiplied by probability of H. So if you write that, and you can always take a log, because log is monotonic. So if you do those two transformations, so basically you will be multiplying this by a log of this by this normal and taking a log. So then the formula comes out to be this, which is lambda H1 plus beta X minus WH whole square. So so this is what we are trying to, every time given an X, we are trying to optimize, find an H that gives a minimum value of this value. And if you think of it as a loss function, then this is a L1 loss. So it imposes sparsity on H. So most of the features on H will be 0. So that way it is also a feature selection. It is also a feature selection method. So and the way, if you see the way the book writes that the training alternates between encoding the data and training the decoder. So the training alternates between H. So W is only used in here. If you see, W is not used in encoding. This method is used like this. This method is being used. W is directly used in decoding, though. Given H, you can find X. So so it says training alternates between encoding the data and training the decoder to better reconstruct the data. So this training is minimization with respect to X and also with respect to W. So that's how this encoding works. Is we are optimizing both on H and on W. And so this one again, because this loss function or this function is an L1 norm on H, it imposes like sparsity on X. So only a few H's will have value. The rest of them will be 0. So it's also a feature selection. And the book says that one thing the book says is nice about this method is that there is no W, there is no specific W for encoding. So every time you are trying to run that algorithm to find H given X, so so if you are given a point that was not seen in the sample data, then this method gives you a better value of h corresponding to that x that was not seen before. So, but the disadvantages of sparse coding are that it's hard to train and requires greater time to compute h. So that's sparse encoding. And also that what the book says is that if you, for example, if you plot h's, so think of this as x, the left side image, the right side image as the corresponding h's. If you plot those, then they are not very representative of x, because each time x is encoded into x, a random subset of features might be used. It might not be like every time that algorithm is run, it might pick up a different feature. So that's why it does not capture the image like if you want to visualize the image, it's not the nicest. It's not the nicest way. If you want to go to that other feature and come back to that original one, then it works better.
Hey, we have another question, Pankaj. Yeah. So the question is sparsity due to the L1 norm in the optimization function?
Yeah. So if you see, we are trying to find argmin of h, where well, it has other terms as well, but if you see, this has a L1 norm of h. So if you like L1 norm generally introduces sparsity in h, because there are multiple ways to explain it. Let me go and maybe explain how L1 norm L1. Okay, this one. I don't see a nice picture, but yeah, this one. So basically, what it's, if I remember this formulation correctly, is that if you, for example, if your loss function, this is the contour of a loss function, then if it's an L1 norm, then it hits. If you see L1 norm from 0 is constant something. So these all squares have the same L1 norm from 0. If you see, so this value and this value have the same L1 norm. So because of this shape, if you have like another function, another value, another loss function that comes and that you are training with, then generally it comes and hits a point which is on the edge. So I'm not saying the exact formulation, but it's something. The argument goes that the optimal point generally has one value that is non-zero, and the other values are 0. So that's why L1 norm, because the contours look like this. Contours means equal valued points. So then it only has one. It induces sparsity. So for example, if the contour was a circle, like in L2 norm, then this line will hit that circle in 2 points. In a point. So if this was a circle, then it might hit somewhere here, which means both an x and y have values. So that's why L1 norm induces sparsity.
Great, thank you.
Hope that answers the question. And yeah, the last topic. The last topic is, I didn't quite go through. So the last topic deals with manifold representation of PCA. So the most prevalent method for in this family is PCA, where you don't really have a noise. you're just trying to get the most variance, get the axis of h. So given a set of points, you're trying to find the axis or the hyperplane which explains the most amount of variance. And so what this says is that plane. So think of it as if x is a three-dimensional, it has three components, then it could be a three-dimensional. It could be represented in a three-dimensional Cartesian space, and then in that space you can have a plane which explains the most amount of variance in x. So that's where you are. So if you see, I think the image came out wrongly, but I'll show it in the book. So in this image, if you see, the max amount of variance is in this direction, in that plane. So in 3 dimensions, the plane is 2D. So here there is a 2D plane, and the most amount of variance is in this direction. So that's where you project your x's, and that's what is I guess that's what manifold interpretation. That's called a manifold plane, and then orthogonal to that is another plane, which is orthogonal to that means this plane, let's suppose, is represented by this vector. Then the other axis with the max variation, the second axis with the maximum variation, would be this one, for example. So this will represent the plane coming out of it, like this. So you project your x into these hyperplanes, and then you get a lower dimensional representation of your data. So that can take a x. That can take your x to a h. So that's, I don't know if I explained it very well, but for example, x is a 3D point, and you want to, and h is a so if your data set, all the points x, you find out that the maximum variation is in this plane, then you project your new x to that plane, and the vector that you get, which is a lower dimensional vector, you can say that it represents, it kind of encodes x. And also that if you take all these axes that have non-zero variation here, then you will basically reconstruct the whole point given x. So this is what classic PCA is like. It's a good concept. If you want to learn it, there are multiple. It's very popular, and yeah. So I guess that's about it for this chapter.
Great. Thank you, Pankaj. Yeah, there weren't any other questions in the chat. We do encourage, if there are any other questions, we can open the floor for open discussion on this topic or in general, the deep learning book. Our presenters are happy to answer questions based on what they know, and they're happy to share their prior experience as well. So while we're waiting to see if there are any other questions, I just want to remind people that are just joining us for the first time. So this is our online discussion of the deep learning book, part of the AI and deep learning enthusiasts meetup group and Facebook group. So we host these sessions every week, usually on Saturday. Today we hosted on Sunday due to a family emergency, but still glad that you guys could be here and join us today. And if you'd like to kind of get involved with our group, we do encourage that. We do host these online. We also host them in person in San Francisco at Sandbox Suites every week. And if you'd like to sign up to volunteer to be a presenter, if you just go on our meetup page, or also there's a link in the description of the YouTube page, which has the presenter sign up form. You can just go, there's 2 tabs on the sheet, and one says for online, one says for San Francisco, and you can just put your name next to a chapter. We also encourage the people that do a presentation to link a copy of their slides or presentation for us, and any additional resources. And I recently decided I'm going to start actually compiling all of these into a repository on GitHub. So I'm going to share my screen really quickly just to show everyone. In the meantime, here, let's do this really fast. Share screen. Okay, so if you guys go to GitHub, and then you look up Excel AI GitHub, and then there's a repository called AI/DL/enthusiast meetup. And I just think it would be a great way for us to just get all these resources together in one place and kind of help each other learn and grow through, kind of like an open source community project. So if you click on Deep Learning Book Review, I already started for chapter 1 and 2, which is the one I originally presented on quite a while back now. And what I have here, the way I started it is just a markdown file with the presentation slides, a link to the online discussion, a YouTube video, and then also additional resources. And it would be nice if there are sections that we start adding code to as well, that we could also link them in this repository, just to make it a better learning experience for anyone starting this book for the first time that wants additional resources or would like help to supplement their learning experience. So if you guys would like to join that, that would be great, and we can just have everyone contribute and just kind of help each other learn and grow. So we do have some more questions in the chat. Let's see. So Sharif has asked, would you say these techniques are still popular today? What do you think, Pankaj?
I don't think so, because the book, one of the sections, the author mentions that linear factor models, like all other, this linear factor model, like all other linear factor models, is not very popular. The one that I was explaining, that it's not very popular because it assumes a slow prior. It also says that none of the other ones are very popular. So I guess none of them are very popular, but it's I guess PCA is very popular. PCA is used a lot, but I think the deep learning, like the deep neural nets, automatically find the features. I don't think we use the more complex methods to find the features.
Great. And then another question here. Is there any relation between sparse coding with sparse autoencoders?
I think so. I think this is just sparse coding is just a segue into the next chapter, which is autoencoders.
Okay, great. So those are the only other 2 additional questions. Did you have anything else you wanted to discuss, Pankaj, before we end this call?
Yeah. So if you guys like, I've been working on this product called Data Cabinet, and we are running a beta. So if you guys like to keep your notebooks on the cloud and with the Conda environments, do sign up for our beta. The website is datacabinet.info, and you can sign up for a beta, and we can send you an access code, and you can keep your notebooks on the cloud as well.
Great. Do you want to show them the site? Do you want to just go to datacabinet.info and show them the site really quickly and how to sign up?
Yeah. So if you sign up, you just go and give us your email address here. Then we can send you an access code, and then you can keep your Jupyter notebooks and Conda environments in the cloud in AWS directly, and it has some very nice sharing features as well. So it would be nice if you can try it out and give us some feedback.
Wonderful. Thank you, Pankaj. And that is something we encourage. If you guys are working on projects, or if you have a product or a company you're trying to start, we do really want to help out our community and our presenters as well. So we would love to share their projects and share their information and give them feedback. And just like us at the AI and Deep Learning Enthusiasts and Excel AI, we also really appreciate your feedback as well. So thank you for joining us today. Thank you, Pankaj, so much for doing the presentation for us and putting all that material together. We'll be sharing the links to his presentation as well, both on that Excel spreadsheet as well as in the repository that we just started on GitHub, so the Excel AI, AI Deep Learning Enthusiast Meetup repository. And I'll be adding all the previous links that were included in that Excel spreadsheet to that repository. And we do encourage the community to add more and just make it an open source community project to kind of gather all these learning resources. So thank you very much. Thank you for joining us, and we'll be signing off.
Thank you. Thank you, everyone. Thank you, Laura.
Okay, have a good day.
You too.